Hey class, so in this first video I'm going to give you just a brief overview of all of chapter 14 so that you can kind of see where Jacobs is going with his argument here. He's going to start off talking about, as you can see here, regular polygons, like these lovely hexagons in the beehive. And then he's going to connect this back to circles, as we've been talking about for the last two chapters. So I want to make sure you understand where he's going with it, so you understand why are we talking about polygons right now, and then what does the area of polygon have to do with the rest of this chapter about circles. Okay, so he's going to start off with regular polygons, and regular might seem like an odd choice of words, but it just means that they have equal sides and equal angles, like these lovely snowflakes. So he's going to talk about regular polygons, and the important thing here really is that every regular polygon is cyclic. So just as we were talking about in the previous chapter, if something is cyclic, then you can circumscribe it. You can draw a circle around it that will contain all of its vertices. And that'll be really, really important for the concepts we're looking at in this chapter. The fact that these regular polygons are cyclic. They can be inscribed in a circle. Because the thing with regular polygons is, being that they are regularly shaped like this, it's really easy to divide them up into triangles, and we know how to find the area and perimeter of triangles. So by breaking these regular polygons into triangles, we're able to find a formula that will give us then the area and perimeter of any regular polygon, just based on the number of sides that it has. Don't get panicked by these formulas. I will give you all the formulas that you need on the test. You don't have to memorize them. And I'm going to go ahead and just eliminate the ones that involve sine for your sanity. Okay, and mine. But we use these 30, 60, 90 right triangles that we learned about in chapter 11 to find the area formula for these regular polygons. And then from that, no matter how many sides we have, we can just substitute in the number of sides, and that allows us to find the total area, okay? Because we're just breaking it into the number of triangles that we form from it, finding the area of each triangle, adding those all up. Okay, so since triangles allowed us to find the area and perimeter of any regular polygon, the regular polygons can be pretty useful for us. And what Archimedes, the great Greek mathematician, discovered is, if I can inscribe this regular polygon in a circle, and I can find the area and perimeter of the regular polygon, I can probably come pretty close to finding the area and perimeter of a circle. Okay, which is something they couldn't do prior to this. Because the cool thing is, as we see, and that's why I'm showing you the book instead of attempting to draw these, because it'd be really hard. When you get a lot of sides, and this one is just 20 sides. This isn't 100 or 1,000. This is just 20 sides, but at 20 sides, this figure is pretty close to a circle. So Archimedes figured if he can find the area and perimeter of that figure, that's a pretty good estimate, at least, for the area of a circle. Okay, and so that's the process that he went through. So he starts by inscribing. This is why we talked about inscribing and circumscribing in chapter 13. He starts by inscribing a hexagon in a circle. It's like, okay, that's pretty close. But then he takes each of these points and he says, well, let me draw two more lines here. I'll put a vertex here and draw a line that goes here and here. So now there's two more sides. So now we have a dodecagon. We have 12 sides. So he's just doubled the number of sides in this figure. Now make it this, and look at how much closer that is to approximating a circle. Okay, but still, we just use that same formula. Instead of putting in 6 for n, we put in 12 for n. And that same formula is going to give us this number. So you see, when there's 6 sides, when you plug in 6, you get about 3. When you plug in 12, now you get 3.10588285, and keeps going. When you get to 24, which looks awfully close to a circle, you can see that then we're at 3.13. When we bump it up to 48 sides, we're at 3.139. And as you keep increasing your sides to where you really can't, I mean, even with 48 sides, you can barely tell that that's not a circle. But if you get up to, say, 3,000 sides, this looks remarkably close to pi. So our basic formula for a regular polygon is 2 times that 180 over the number of sides times the sine, that whole thing, times the radius of the polygon, because regular polygons still have a radius, okay, the distance from the center to the corner, to the vertex that's inscribed on the circle. And so as you get closer and closer to the shape of a circle, your increasing sides, this number, as you divide by larger and larger numbers of n, that number gets closer and closer to that value that we know as pi. So that's how Archimedes and then later mathematicians such as Liu Hui, that's how mathematicians found pi, is by inscribing regular polygons in circles, calculating the area, and then saying, let's try it with more sides. Let's try it with more sides until we get closer and closer to a circle. So that's what we're trying to do here, is we're starting with regular polygons. We're finding the area and perimeter of those polygons, and then moving to how that allowed us to find pi. So then we can find the area and perimeter of circles. Okay, so lesson 5, we're getting into the area of circles. You can see that there. And then lesson 6, we're just going to look at sectors and arcs of circles. So like pi pieces of circles. Okay, and that's something that comes up commonly on the SAT. It's pretty easy once you've done it. So it's a helpful one for us to do. And then that should be, yep, the end of the chapter. Okay, so I'm working on modifying this down for us due to our circumstances and our time frame. But we're going to focus on things like every regular polygon is cyclic. How did we find what pi is? And then formulas for for circumference and area of circles, which I think you already know. 2 pi r for the circumference, pi r squared for the radius. And that's really what we're looking at for chapter 14. How are we going from polygons to circles? And those concepts of inscribed and circumscribed, how do those help to make that connection? Okay, so that's our basic idea for chapter 14. I'll go through and make individual videos for the lessons. And then I'm going to just work on modifying the homework a little bit for our circumstances. Okay, thanks guys.